as we proceed forward then with number 10. Okay, and it goes on to state, okay, the energy used to power the Apollo lunar missions was supplied by the reaction below. For the phase of the mission, when the lunar module ascended from the surface of the moon, the total of 1,200 kilograms of N2H4 will available to react with 1,000 kilograms of CH3 parenthesis 2 N2H2 and 4,500 kilograms of N2O4. For this portion of the flight, which of the allocated portions was used up first? So when we say it's used up first, that is your limiting reactant. What's different about this equation so far might be what? You got 3 reactants instead of 2. So how much water in kilograms is put into the lunar atmosphere through this reaction? Okay, so first of all, it looks to me like you were given your balanced chemical reaction. I left a couple markers over here because we're getting ready for next week. Do you feel cheated that this class is in the afternoon? Because if there's late starts, you never miss this class. Okay. Okay. Fair enough. Okay. So what we see happening then, we've got our balanced chemical reaction of 2N2H4. Okay. And we've got plus CH3 parenthesis 2 N2H2. Okay. And then so we already know that this might be the second portion, but regardless, then we've got 6 and 2. And okay, so the very first thing to help yourself out the most would be what? Above each one of these, how much you actually have. Even if you didn't do it right away, that's fine. But the first thing you're going to do is change these numbers to what first? No, it's already in grams. Well, you can change to kilograms, yes. But then once you have it in grams, then you're going to change them all to moles. Okay, so with that, let's go ahead and we've got 1,200,000, okay, grams of this substance. Then we've got 1 million grams of that. And then we've got 4.5 million grams. Okay. Of that final substance there. So you correctly said the very first thing you're going to do is change these to moles. So let's go ahead and proceed doing that. Okay, so we've got, yeah, we can still see that. 1,200,000 grams of N2H4. Okay, so obviously we're going to have really, really large numbers of moles. That's axiomatic because that number is so big. So for every mole of N2H4, we get 32. Okay. That's right. Okay. N2H4. Okay. So then when we calculate that out, 37,499 then this is going to be labeled in what, though? No. Moles of N2H4. And what's significant about that number in reference to N2H4? That's how much what? We're not that far yet. So let's just go ahead and write it underneath here. 37,499 moles of this substance, because that's how much we actually have. Okay? Then change another one of these to moles, and it doesn't matter which one you pick. We're just going straight across here. So now we've got 1,000,000 grams of, I'm just going to abbreviate that as dimethyl hydrazine. I believe that's what that would be. So DMH is this compound right here. That might be kind of hard to see. I better change colors. Okay, change it to purple. So when we add all them together, for every mole of DMH, we get 60.12 grams of DMH. Okay? Are we following along so far? All right. This is worth some people's time, it looks like. Okay. 16,633 mole of DMH. So we'll go ahead and put 16,633 moles of that substance underneath, so we know we have that amount. And hopefully you're writing small enough, because I knew this would take a long time to get through this problem. We'll go ahead and do that final line, that way we can erase all that information. So then the bottom one, we have 4.5 million grams of N2O4. So for every mole of N2O4, we have 92.02 grams of N2O4. I was thinking that had to be moles. And when we calculate that out, we get 48,000. My writing's so small, I got to double check as well. 48902.4. Okay, and that's moles of N2O4. So now we can take that number and write it here, 48,902.40 moles of that substance. So now, we see how we got those three numbers in moles, so these calculations can now be erased. Okay. So now what you can do is remember, now that we have our three substances here, the clue that we gave is do what? Just take one substance and convert it to moles of another one. That's all you're doing. So if you just want to go in a logical order, there's nothing wrong with that. It's whatever you feel the most comfortable with doing. And for instance, I think when I worked through this, I just worked from left to right. So if we have 37,499 moles of N2H4. We're going to convert that to what then? Okay. Well, you can, but yeah, if we're working left to right, we're going to convert this substance into this one to see, compare what is required to what we actually have. This is just a little bit different. I mean, we're solving this the exact same way. So for every mole of this substance, N2H4, okay, we're going to get a mole. Now, if you chose to do it that way, you're going to get the same answer, okay? But this is how we're going to go through this process. So that's what I meant. We're just going to work from left to right. So again, that's dimethylhydrazine. We know that's that substance right there. We've got a mole ratio. So what does that mean? Okay, so we go back to our balanced chemical reaction. We've got a 2 there, and a 1 here. So what do you get when you divide them two out? Let you catch up. 18,624. Yeah, we knew what you meant. Right? 18624.91. You just had a befuddled look on your face like, this here, it's 37,499. Okay, so if we back up, if we take 1,200,000 grams, okay, divide that by 32. Okay. So 1,200,000 divided by 30, what did I say, 32.06. Okay, 37,429. Okay. Yeah, that's probably a good reason not to do this in pen. Okay, so that's going to change this, not a terrible amount, but still when we get all that wrote out, it's going to be 18,624 mole of DMH. And then what's the next thing we want to do is write okay, 18704 18714. Okay. So then when we did these problems prior to this day, this week, once we find how much of this is what, we compare back to that. We write these three letters. REQ. That's how much is required. So when we compare that back to this, okay, so we can write 18,714. So if we just had two reactants, we could say we've already found our limiting reactant. But we don't know if that's going to be the one that runs out first because we're dealing with 3 of these reactants, not 2. So is everyone following that logic? This is how much we have. That's how much is required. Okay. So then let's just move further on down the line. We can just go ahead and take this and convert it to this substance to see once how much is required. Okay? Because we had to do 2 of them anyway. All right? So, in this process, we will take 37429 moles of N2H4. In case you're wondering, is this a problem that was just made up just to torture you? Well, maybe yes, maybe no. But this was one of those in the back of the chapter that the author chooses to assign. I mean, rather than making you do it on your own. That's why we're working on this together. So notice we converted this substance to this one. Now we're going to convert this substance to this one. So this is still the same, mole of N2H4. So what's going to go on top now? N2O4. Okay? And like you correctly said, we got a 3 on top and 2 on the bottom. So when we punch that figure out, it's approximately 5, 6, 1, 3, 4, 5. Okay, mole of N2O4 is what? These 3 letters again. We would write REQ. Okay, so now we can take this number and write it up here and say 5, 6, 1, 4, 3.50. Okay. Well, which one looks like it's a bigger discrepancy so far? This one or this one? This is a bigger discrepancy so far. So we know for sure that it's not this one so far, but just to be safe, we can always double check this and convert moles of this substance. Has to be this one because we've already compared that. Okay, so as we do this final one, okay, 48,000. Yes? 48,000. Okay, 902. Okay, 0.40 mole of N2O4. Okay, so now what goes on the bottom here? So, yeah, it's a mole to mole ratio, but what is it? Okay, so what number goes on top? Which one goes on the bottom? 2 here, 3 there. Okay, so when you punch that out, 3206. 32601. Okay, we really don't have to go any further. 32601. Do we have enough of this substance? Remember, this is REQ, required. We can subtract them and still come up with a positive value, correct? We can subtract this one, and it's approximately how much short? You could say 2,000. It's probably not quite 2,000, but we're going to say minus 2,000. Okay? And we subtract these two, it's much easier to see it's how many short. About 8, yeah. We're going to say 7,000 moles short. So the discrepancy is telling you which one of these 3 is going to run out first. You say N2O4. Are we just saying that, or we? Okay. Remember, this is going to be a positive value. We've got oodles and oodles of this substance left over, so that's fine. This one is running a little short, but this one is definitely going to run out first. This is your LR right there. A lot of work, I know. Yes. How many of you have seen the movie The Martian? So yeah, I think it would open everyone's eyes to see how much behind the scenes that them NASA scientists are actually doing. So something like this is what was actually done for the lunar module. I think this was, what do we say, the Apollo, what mission? Oh, it doesn't, lunar mission, so I'm guessing it's probably not the 13th mission because they made a movie about that. It was called The Successful Failure. So it's probably for the Apollo 11 mission. So now that we have our limiting reactant, all of this can be erased now. A lot of work, I know. It's going to be well worth it, we hope. Okay, so if we want to see or calculate how much water we're dumping into the lunar atmosphere, how do we calculate that on this side? Now it's going to be a gram to gram problem. But how do we start it? Yes. Why are we starting with this? But that's true. Which one runs out first? This one does. So that's why it's your limiting reactant. Okay? So, upon doing that, you can start your problem with, you can start it with this number if you wanted to, or which one of these two could you use, the purple or the black? I hear purple, I hear black. This is how much was actually required, so we want to use how much we actually have, which would be the black. Okay, so then, but yes, you could start with 4.5 million, but should you go ahead and decide, well, I'm going to start with this number, you've already eliminated one step, which is fine. You're going to get the same answer whether you start with this one or that one. So we're starting with this number right here. So 48902. Okay. And I'll let you continue. See if you can. Looks like one of us is done already. No? Need a mental break? Yeah. Okay. So we'll give you about 7 minutes, because it won't take us long to wrap up that last little part. In case you're thinking, it's Friday, we shouldn't have to work this hard. Is that true? That's how much water we want to find. And it's asking for how much water in kilograms was put into the lunar atmosphere. For what part? Well, yeah. When you get your answer, are you multiplying or dividing by 1,000 when you have it in grams? You're dividing by 1,000. All you're doing is moving the decimal that last step, so hopefully that's not too intimidating. What did you get, Cole? 2349. 2349. Okay. Okay. So this is moles then of this substance, N2O4. Okay? So we've eliminated this 4-step problem down to 3. So how do we get rid of moles of N2O4? We're converting what we have, which is N2O4, into moles of what we're looking for, which is what? Okay? We've got a mole-to-mole ratio. 8 on the top, 3 on the bottom, because the 8 comes from here, the 3 comes from there, your coefficients. Now we're on the home stretch. Okay? So for every mole of H2O, how many grams do we get? 18.02. Now, that's going to be in grams now. Then that last step you had correctly said, well, for every 1,000 grams, how many kilograms does that give you? 1. Okay? So now all of our labels have canceled. We are now in kilograms of water. So now when we do the number crunching, 3. 3 or 4, yeah. Yeah, 3 or 4. Sounds about right. Your head hurts? Okay. Now, again, this is just whether you can believe this if you want. We're just stating the facts here. What I've noticed or experienced is that, yes, this is tough, but this tends to knock people down, this information, okay? But then when we get to gas stoichiometry, if this didn't finish you off, that certainly can. It doesn't mean that it will, but it means it can, because that's a little more difficult than this, okay? 2, 3, 4, 9. Yes. Okay. So I will collect these in a moment. So on Monday, now keep this in mind. Whether we're going to have school or not, which we probably should. There's really no reason to believe that school is going to be canceled. But it's that time of year to where sometimes it's a toss-up if the weather's going to allow us to come to school safely. So with that, we're all right if we miss one day. Okay, we're all right so far, because I have it scheduled that we would review on Monday, have our second problem quiz in here on Tuesday, and then on approximately Thursday, Friday if we miss school, but approximately on Thursday, we're going to take information, not numbers this big or complex, but go over into the lab, and 1, you calculate your limiting reactant, what's going to limit what you can produce. 2, you're going to calculate your percent yield, okay? What that would possibly mean is on pencil and paper, you calculate which yield, percent or theoretical first. What you theoretically should come up with on pencil and paper first. Then you separate your precipitate. What's a precipitate? Yeah, the insoluble substance on the bottom. Once you get that separated out, that's what you actually produced. You compare that to what you theoretically should have come up with, and then that gives you your percent yield. That's next week, so hopefully the weather is kind to us. Let's keep our fingers crossed. So we'll pick up with this next week.